This is a demo of Matsu Analysis, a tool that we at Open Data Research have developed to browse hyperspectral satellite images as a first step in deciding how to train on them. Now, I say that these are hyperspectral satellite images, and that means that in addition to the ordinary red, green, and blue that normal images would have, these have literally hundreds of bands that are just numbered. The tool starts by showing you a single satellite image. In this case, this is a bit of the Amazon rainforest with obvious human development in these rectangular bits. And to get a sense of what this image might contain, let me just change the red band from canonical red, which is 29, to some other bands within the original image. I change it to 36. It looks very different because now the red that I'm injecting into this image is coming from something that has a higher wavelength, more toward the infrared. I could go an extreme in this direction, say 90. And that's beginning to dominate. Let me go all the way to the end, 217, I mean. Now the red is a whole lot weaker because you're starting to see the tail of the distribution of incident light, which is not uniform because the sun has a finite temperature. Okay, let me go back to 29. Now, we can do more detailed studies with the panel on the left. The way that we do that is first, in the master image, we double-click or drag to pick some sub-selection, and then take a look at it with the false color image. Later, we will make this actually false color by changing what the bands contain, much as we did in the master image here. Now let's also get a spectrum. And here we can see from the lowest wavelength band to the highest wavelength band how much average radiance is contained in each. And that's an average over all of the pixels contained in the box. So if I were to put the box into one of these human habited regions, I get a different looking spectrum than if I put it out in the rank wilderness. See, it's the jungle that's giving us this shape of going down and then up, whereas the human habitation is more flat. Okay, let's go back to this because it's more interesting. This bottom panel will show us a distribution between two bands. By default, 29 and 16, but those are randomly chosen. By distribution, I mean, unlike the spectrum, which is showing us an average of all pixels within the box for all bands, this is showing us for two bands each pixel and how they're related. So in this case, each of the pixels, band 29 is well correlated with band 16, so that even though they both vary by more than a factor of 2, they are highly correlated, so you get a sequence, a long thin line of them. Some other bands, such as, say, band 40 and band 29, have a very different structure. So here you can see the linear sequence, which is coming from pixels that have the same color but different intensity. And then we have another completely different linear sequence here, where this is just a different color from that. And by color, I mean it in a general sense. between all the hundreds of primary colors that the hyperspectral camera is giving us. So we can use this information to start to do some remedial classifications within the tool itself. Because in each of these boxes, we can put not just a band name, but actual code. So let me say band 40 minus band 29 over band 40 plus band 29. And the reason for that combination is I want to normalize out the absolute intensity and see the differences between them. And that horizontal axis is showing us the distribution. Now I can take that same combination and I can go back up into this false color image, and now let's keep it true to its name. Let's make it actually false. And I'm going to put the same combination in for all three bands, so I'm going to make a black and white image. And here we see that this combination that distinguishes between, let me put it back here, BO40, BO29, that distinguishes between these different slopes by taking differences, is showing us the difference between the jungle and the human habitation. And then having trained our expectations on this corner of human habitation, let's look at it down on this corner and see if the same thing holds. And it does. These are dark. In fact, it's really highlighting these bits of trees among the human habitation more than the RGB image did. Because when humans take over a place, they do still plant trees. So you can see that this could be used to study things in greater detail, although from personal experience, you end up spending some half hours to hours playing with it before finding something interesting. I'm going to keep this video short. But then when you've gotten past the point of doing all that you can do interactively, you can still make use of the regions that you've selected because you can get all of the numerical data that's plotted on the screen through these text boxes. And as a first run of the machine learning phase, where you're actually using some machine learning software, you can copy and paste this into the learner. But then beyond that, you would have to go to the original image itself to do a full analysis.